Okay, so we're going to look at properties of solids, and then we'll focus on the other phases of matter that we talk about here in AP chemistry. There are other phases of matter like Bose-Einstein condensate and plasma and that sort of thing. And if you take physics or some advanced chemistry courses in college, you might end up talking about those. But when we are dealing with AP Chem, we just stick with the solids, liquids, and gases. So we talked about last time the intermolecular forces and the fact that different intermolecular forces exist with they're what cause our material to have the different states. Okay, if you have really strong intermolecular forces, then you're dealing with a solid. If you have kind of weakish intermolecular forces, then you're dealing with a liquid. And if you have virtually no intermolecular forces or no intermolecular forces at all, then you're dealing with a gas. So as you weaken the intermolecular forces, you change phases. And that's essentially what the energy is going in to do during those phase changes, is to weaken these intermolecular forces. So when we look at these, we're looking at we're starting to look at essentially like structure of ionic compounds. And when we talk about ionic compounds, these are compounds where we have the different ions of opposite charge. They're coming together, they're getting attracted to one another. And that's going to create this crystal lattice structure. So it's very strong. And that's why your ionic compounds at room temperature are always solids. They're collectively referred to as salts. So it's not just sodium chloride that's a salt, but every one of these would be salt. They're not ductile or malleable. And the reason why is because when they end up trying to hit them and try to flatten them out, the like charges come together and they repel, and then the solid splits apart. So they have strong electrostatic forces of these oppositely charged particles, which results in high melting point and boiling point, low volatility. So even if we heat them up high enough to get them into a liquid state, they're not going to be transforming very easily into the gaseous state and back down. And so since they have low volatility, they don't put much pressure on the container that they're in. So that makes them also have low vapor pressure. As a solid, they are not free to move. They're locked into this structure. But if we go into a liquid form or if we dissolve them into a solution, then those ions are free to move and they will conduct electricity because they have a charge associated with them. Covalent compounds you can get to dissolve in liquids into a solution, but because they don't have a charge associated with them, they don't carry electricity. In the ionic structure, that lattice then is going to be held together by those electrostatic attractions. The strong bonds are going to give it that high melting point and very high boiling point. The low volatility, vapor pressure, same deal. And then the conductivity that we just talked about. So when we dissolve ionic solids, they will dissolve in polar liquids. And they do that because they are charged. And I showed you that in the previous video, how the negative part will go to the hydrogens in the water, and the positive ion will be attracted to the oxygens in the water. And that's where that idea of like dissolves like. Do not put like dissolves like on a test. You will get it marked wrong. You have to explain it in terms of polarity. Okay, that process where we're breaking down those ions is called hydration, and they're said to be hydrated. The ions then become free to move once they're in the hydrated state, and that makes them a good conductor of electricity. Nonpolar solvents, though, will not be attracted to ions, and that's because they don't have a charge. They're not going to be attracted because there's no charge there. It's like holding up a magnet to, a piece of wood. It just doesn't work. Okay. So polar water molecules are going to be attracted to the opposite charge that penetrates that lattice, starts breaking those pieces off of the lattice. Each ion gets pulled apart, and eventually they disassociate. And you either run into one of two situations. You either run into a situation where you run out of the salt and run out of those ions and you have water left over, or you run out of water and then you have ions left over. Well, they're going to stay in that solid form and they'll sink to the bottom. So that would be a saturated solution. There is a difference between a saturated solution and a supersaturated solution. A supersaturated solution is a rare case. Acetate, sodium acetate is one of the classic examples of it. It does not happen with most substances, though. So don't say, well, it had too much solid in it and it settled to the bottom. It's called supersaturated. No, it is not. Nonpolar solvents, then, no charged ends, so no attraction or penetration of those ions. They're just going to stay together in a clump, and so that's why it does not dissolve. So here's a kind of depiction of that, where we have our sodium chloride here. They're pulling off the individual ions, the chlorines here. We've got our water surrounding it with a hydrogen on this side. And then on this side, we've got our sodium. The oxygens are surrounding it because they're oppositely charged. Okay, here's another kind of depiction of the same thing. Slowly, eventually, you'll pull it off and everything will get surrounded. Okay. And we'll talk about that as far as entropy and disorder of a system and everything when we get into, it's called Big Idea 5 is what it used to be called, but now I think it's Unit 6 that we talk about that. Group 14 elements, then we talked about these last unit. We talked about allotropes, the diamonds and the graphite, these giant network covalent solids. Silicon dioxide, like your sand, silicon carbide are all examples of that as well. So allotropes means that we have different forms, but it's the same chemical formula. So for carbon allotropes, we would have graphite and diamond, and it just depends on how they are arranged. So here we have diamond, and it's arranged in a very structured form here, very strong. It used to be diamond was the strongest substance known to man. I think they've made like something else that's stronger now, but it's man-made. So this is the natural substance, the strongest one that we know about. So we have these rigid bond angles here, very high melting point, very high boiling point. If we shift our attention over to graphite, again, this graphite is in sheets, and so it's easy to kind of shed one of these layers off. And essentially what you're doing when you do that, when you're writing, is you're shedding off sheets of this graphite and leaving that behind on the paper. So it's going to conduct electricity, but only in one plane. And that's because there's these free outer electrons on the carbon. And they're delocalized, kind of leading to a sea of electrons along one plane. But they can't move between layers. So unless you just had a plane of it, it wouldn't work. This graphite then is also used as a lubricant because these sheets do spread out. And so if you've got a situation where you don't want to have oil on something, but you need to have a lubricant, graphite is often one that people will choose. Some silicon and semiconductors, then we talked about this doping last chapter, so you can kind of go back and look at the notes on that if you'd like. Just dealing with different electrons and how they end up introducing those in. Molecular solids then tend to have a lower boiling point, lower melting point. They don't conduct electricity because they don't have a charge associated with them. Again, similar lattice structure to NaCl, but because of the weak dispersion forces here, there's no hydrogen bonding, there's no polarity, nothing like that. So because of that, it has a very low melting point. And it's a non-conductor. Then we had alloys. I believe we briefly touched on those before too. Mixtures of metals, no metallic compounds. because by definition a compound has a fixed ratio of elements, that's why they don't consider it a metallic compound. It's just a metal. And an alloy is a mixture of a metal. So because of that, it's not a compound, because you could have different mixtures of these. And if you go out to like Wikipedia or out to the internet, you can see that there's different mixtures. So we could have like gold, for example. You have 10 karat gold and 14 karat gold and 24 karat gold. The difference is how much of the stuff is mixed in there. And so since it's not in a fixed proportion due to sharing of electrons, they are in a sea of electrons. Because it's not in a fixed proportion, they don't consider it to be a compound. We have the interstitial alloys, remember, and the substitutional. And again, we've talked about these, so I'm not going to spend much time on those. But here was a picture of those, if you remember, where we have the pure metal. Substitutional, they tend to be about the same size, and interstitial, they fill in these interstices. All right. So if we look at these ionic, if you look at the, let me just skip ahead here. There we go. So the next topic that we're going to talk about is solids, liquids, and gases. And they represent the difference between those. We're going to talk about gas phases and solid phases and liquid phases and use a particulate level to be able to talk about that. All right, so what are the differences? Solids have a definite shape, a definite volume. They're packed tightly close together, and they vibrate in a fixed position. So they can't leave that fixed position. They're stuck there. Liquids take the shape of their own container. Now, the difference between these is that these have stronger intermolecular forces than these do. Okay, so because of that, they don't have a shape, but they still have a volume. So they still have some intermolecular forces, just not as many as they did when they were in the solid state. Because the intermolecular forces are weaker, those particles can flow past one another. And then if we weaken those or get rid of them altogether, then we're talking about gases. So gases have no definite shape, no definite volume. They spread out to fill their container as far and as wide as they can go. So that's kind of the difference between those three. Just kind of another summary of that. And then if you look at that particulate diagram like they wanted us to, you can see that these are vibrating in place, these are close to each other, and then these are spread out. So solids fall into kind of two categories: crystalline solids, where they have a regular ordered arrangement, 3D structure. Those were the ones that we were looking at before, where you could see the definite order of them. And then we have amorphous solids, so wax, tar, glass, all of these are amorphous solids. They don't have that rigid structure, and so over time they're able to move. But they're still considered solid because they still have a fixed volume and a fixed shape. They have very little energy compared to one another, and then they vibrate in those fixed positions. So liquids then are pretty close together. They still have intermolecular forces, and they're constantly moving, colliding. And since the solids and liquids tend to have their own particles very close together, their volumes are often very similar to one another. In a gas, though, the particles possess enough energy to overcome those intermolecular forces, and they're able to move around freely and with large spaces between them. So the liquid is going to be kind of that intermediate state between the ordered solid and the low energy solid and the really disordered high energy of a gas. Just as a side note, liquids and gases are considered to be fluids. Typically you think of just a liquid as a fluid, but gas is also considered to be a fluid, and that's because it has the ability to flow. So that in chemistry is what we consider to be the definition of a fluid. It has the ability to flow. So gas and liquids both have that ability. When we're looking at properties of solids and liquids. Solids and liquids have viscosity. Um, Surface tension, we talked about both of those earlier in the IMF discussion. I don't know if we touched on viscosity, but viscosity is the resistance to flow. So when you're talking about like syrup, maple syrup, or tar or something like that, it's going to be a very viscous substance. Oil, and when it's cold, oil will be like that. So they talk about like wear and tear on your car engine when it's cold, and it hasn't. I don't think that it's a big deal with the newer cars, but back when I was a kid, we would always warm our cars up, and it was to get that oil heated up so that the engine could handle the strain that you put on it when you try to put it into gear and go. But I think they've gotten past a lot of that with the newer engineering techniques that they have. But oil can have a tendency to be viscous. People who drive diesel trucks, a lot of times in the winter, they will keep them running, like when they run inside and that sort of thing, because the diesel fuel tends to be very viscous and works better if it's heated. So that's another kind of practical application or something that you would see out there in the world as far as viscosity is concerned. So they tend to also, the liquids are attracted to one another. They have very strong interparticular forces, and they're likely to be more viscous than ones where their attractions are weaker. So weaker IMFs tend to be less viscous than stronger IMFs. Here is a heating and cooling curve. And again, one of the things that you really need to note, and we talked about this in regular chem, was during a phase change, we do not change temperature. And this heating and cooling curve shows you that. What is happening during this phase change is that the intermolecular forces from a solid to a liquid are weakening. And then as we heat it up, we heat it up, we heat it up, we're weakening those intermolecular forces even more until we get to the point here where we're essentially destroying them. And they're becoming a gas. And then if we cool that gas back down, we reestablish some of those intermolecular forces, we form back into a liquid. And then if we continue to cool that, they will increase even more, and then that'll be where we would end up going into a solid phase. So oftentimes you will see one of these heating and cooling curves without any of the blue information in here, and you have to be able to figure out what's going on just based on this heating and cooling curve. And anytime you flatline like this, that means that there's a phase change going on. So just keep that in mind. And that's all we're going to talk about right now. We'll get into ideal gas law in our next video.